What's going on, guys? Let's do this problem right here. The question is asking 12 microcoulomb charge is placed as the origin, a second -8 microcoulomb charges placed 1 meter, so this is 1 meter to the right of the first, and the third 6 microcoulomb charge is placed 1 meter above the first charge. What is the electric field as x is equal to 1 meter, y is equal to 1 meter? So let's see how we can find this one. First of all, let's draw the diagram. So if I draw the diagram for this one, this is going to be something like this. So here we have, so first of all they are saying we have a 12 microcoulomb charge is placed at the origin. So it means we have a plus charge right here, and this is first one, right? So first one, and the second one is saying a -8 microcoulomb charge is placed 1 meter to the right of the first. So a negative charge is placed right here. It's 1 meter right. So the distance is 1 meter. And they are saying a third one is placed above the first charge, right? So third 6, that is 6 microcoulomb. A third 6 microcoulomb charge is placed 1 meter above the first charge. So this distance is 1 meter. So now we have all the information, and they are asking to find the electric field at x is equal to 1, y is equal to 1. So x is equal to 1, y is equal to 1 mean right here, this point right here. So this is the point we have to find the electric field. So let's see how we can find it. So first of all, we have to know how does the electric field is going to be react in each of the charges. For a positive charge, it always electric field always emit outside. So this is going to be emitting outside right here. And for this one, same thing. For a positive, emits outside. And here we have a negative. For a negative, it emits inside. So we can determine the directions according to this. So for this one right here, this is going to be going this way, right? And for this one, it's going along this way. For a negative charge, it's going toward this, right? Toward this, and this is our E1, and this is our E2 and E3, right? So these are the three electric fields. If you find the net electric field, that's going to be the net electric field right here. So let's calculate these things separately first, and finally find the net one. Okay, first of all, I grab this E1 right here. So first of all, we have to know the distance of this one. This is if this is 1 and the height is 1, according to Pythagorean theorem, this is going to be √2, right? Now we can calculate this one. So let's choose this equation. We know, because we know the charge for everything. For this one it's 12 microcoulomb. For this one it's -8.0 microcoulomb. For this one it's 6 microcoulomb. Now let's use the equation for the first one. So E1 is going to be equal to KQ square, KQ1 R1 square. Here K is always constant, that is 10 times 9 by 10 to the power of 9 Newton meter square over Coulomb square, multiplied by the charge, that is 12 times 10 to the power of -6, because micro is 10 to the power of -6, so 12 times 10 to the power of -6 Coulomb, divided by the distance, that is √2. So from here to here it's √2, so √2 meters square. And if you calculate this value, this one gives you 54,000 Newton per Coulomb. So this is our E1. Let's calculate the E2. So if I grab this E2 right here, that is 9 times, same equation, 9 times 10 to the power of 9 Newton meter square per Coulomb square, times the charge, that is, I'm taking the magnitude first, so this is, I'm choosing the plus one, so plus 8 times 10 to the power of -6 Coulomb in the bottom we are going to have the distance, that is 1 meter, 1 meter square. And if you calculate this value, that will give you 72,000 Newton per coulomb. Right, let's do the third one. So the third one is 6 microcoulomb. So 6 microcoulomb, so only difference is 6 microcoulomb instead of this, because distance is also is 1 meter for this one. So let's do this one right here. 9 times 10 to the power of 9 Newton meter square per coulomb square times 6 times 10 to the power of minus 6 coulomb divided by 1 meter square. And if you calculate this value, this one comes out to be 54,000 Newton per coulomb. And if you notice E1 is not in the x-axis or y-axis. So we had to find the components of this one. So this one going to get E1x, E1y, and E1x. So let's find out the components. And also, you know, this is a 1 meter distance. So we know the angle that is making is going to be 45 degree. Since this is equal distance, height and the length, right? So we can find out that one too. So we know that this is 45 degree and this also 45 degree. So 45 degree, 45 degree, let's see how we can find it. So it's gonna be, now it's the E1x is, calculating E1x is becoming easier, because if it's 45 degree we just have to multiply by 45 degree, and both of them going to give us same answer, because sine 45 and cos 45 are same values. So let's calculate this one. So we have E1, that is 5,400, 54,000, right? 54,000 times cos 45, that's going to give us 38,000 Newton per coulomb. And let's calculate E1y, it's going to be same thing, 54,000 sine 45, and that's going to give you 38,000 too. Now we can add all the x components. So E total x component is going to be simply E1x 38,000 plus this x component. We have E3 also in the x component, so we have to add that one. So this is 54,000. That gives us 92,000 Newton per coulomb. So this is our x component. Let's calculate the y component. So let's continue here maybe, yeah. So ETY. So ETY, we have E2 and the E1y. E1y is in the upper direction, because this arrow is going away from this plus sign, so it's going to the upper direction. The component is upper direction, so E1y is upper direction, so it's going to be positive. E1y 38,000 we calculated right here. Then E2 is in the down, so it's going to be negative. E2 is negative, and the value of the E2 is 72,000, so it's going to be negative 72,000. And if you calculate this one gives you 34,000 Newton per coulomb. Now we are almost reached at the final thing. We have x component and y components together. So now we can write this one into vector form as 92,000 Newton per coulomb x components, 34,000 Newton per coulomb y components. And if you want to calculate the magnitude, you have to square and square root it, right? Square and square root it. So magnitude of this one is going to be simply square root of 92,000. This is 1000 right here. 92,000 square plus minus 34,000 square. and if you calculate this one comes out to be 98,000 Newton per coulomb, and that is the final answer for this question. What is the electric field at x1 y1? This is the answer. So this is how we do these kind of problems. I hope you guys liked this video. See you next time.